Welcome everyone.
Question number 101. The mechanism method and the statistical method give upper and lower bounds respectively on the strength of structure. Option B is right answer. There are three methods which are used in plastic analysis, and these are mechanism method or kinematic theorem, next statistical method or equilibrium theorem, and the next one is uniqueness method or uniqueness theorem. Question number 102. For the frames with large degree of static indeterminacies, the mechanism method is simpler as compared to statistical method. Option B is right answer. Question number 103. In the T section shown in the figure 13.1, where all dimensions in mm, the distance of plastic neutral axis from the top is. Look, this is the T section given in the question. The flange has a width of 40 mm and thickness 10 mm, whereas wave has a depth of 50 mm and thickness of 10 mm. So the total area will be 40 into 10 plus 50 into 10, which is equal to 900 millimeter square. Okay, and the half of the area will be 450 millimeter square. Okay, and we also know that the area above plastic neutral axis and below plastic neutral axis both equal. Okay, the area above neutral axis, above plastic neutral axis, is equal to the area below plastic neutral axis. Okay, so first of all we have to find out where the plastic neutral axis lies. Okay, so half of the section area will be 450 millimeter square, and the flange area is 40 into 10, which is equal to 400 millimeter square. So clearly we can say the plastic neutral axis lies below the flange portion. Suppose this is the plastic neutral axis. Okay, the area above this neutral axis is equal to the area below this neutral axis. Okay, so we can write y into 10, y this thickness 10 plus y into thickness 10 plus 40 into 10 equal to half the area 450 millimeter square. So from here we can get y equal to 5 mm. So plastic neutral axis from top will be 5 plus 10, 15 mm. Option B is right answer. Question number 104. The effect of axial force and shear force on the plastic moment capacity of a section are to decrease the plastic moment capacity in both cases. Option D is right answer. Question number 105. If a structure is statically indeterminate to second degree, then the maximum number of plastic hinges required to render the structure a mechanism is degree of static indeterminacy plus 1. 2 plus 1 equal to 3. Option C is right answer. Question number 106. Which of the following section will have large shape factor? Diamond section will have large shape factor. Option D is right answer. Question number 107. The shape factor for the solid circular section subjected to bending about its diameter is 1.7. Option C is right answer. Question number 108. The plastic section modulus for a rectangular section of width B and depth D is. So this is the rectangular section of width B and depth D. Okay, so the neutral axis passes through the middle of the section. We all know that. So this distance will be D by 2 from here to here, and from here to here this distance will be D by 2. Okay, and total area of the section will be B into D. And we also know that the formula for plastic modulus ZP equal to A by 2 into within bracket y1 plus y2. What is y1 and what is y2? Y1 is the distance between this neutral axis and CG of this portion, and y2 is the distance between the neutral axis and the CG of this bottom portion. Okay, so this distance will be D by 4 and this distance will be also D by 4. So if we put the value into the equation, the plastic section modulus ZP will be equal to BD by 2 within bracket d by 4 plus d by 4. So plastic section modulus Zp will be equal to b d square by 4. Option B is right answer. Question number 109. Load factor is defined as ultimate load by working load. Option C is right answer. Question number 110. The moment curvature relation at a plastic hinge is constant moment for all curvatures. Option C is right answer. Question number 111. Shape factor is a property which depends only on geometry of the section. Option C is right answer. Question number 112. The statistical method of plastic analysis satisfies the equilibrium and plastic moment conditions. Option B is right answer. Question number 113. The mechanism method of plastic analysis satisfies equilibrium and mechanism conditions. Option A is right answer. Plastic section modulus for a circular section of diameter d is. So this is the circular section of diameter capital D. So this is the neutral axis. Okay. Above this neutral axis, the distance from here to here d by 2, and the distance below the neutral axis from here to here, the distance will be d by 2. Okay. So we know the formula for plastic section modulus Zp equal to a by 2 into within bracket y1 plus y2. Okay. So y1 will be the distance between neutral axis and the CG of this above portion, that is equal to 2d by 3 pi. Okay, and similarly y2 will be equal to 2d by 3 pi. Okay, which is the distance between the neutral axis and the CG of this bottom portion. Area pi d square by 4. So if we put the value into this equation, we will get the Zp equal to d cube by 6. D cube by 6. Option C is right answer. Question number 115. Load factor is always greater than factor of safety. Option C is right answer. Question number 116. The ratio of plastic section modulus to the elastic section modulus is always greater than 1. Option C is right answer. Question number 117. Other conditions being same, the load factor in indeterminate structure is more than the load factor in the determinate structure. Option B is right answer. Question number 118. Which of the following conditions is to be satisfied both in elastic and plastic analysis? Equilibrium condition. Option A is right answer. Question number 119. In the virtual work method, the virtual quantity is displacement. Option A is right answer. Question number 120. Look at the prop cantilever beam of uniformly distributed load W per unit length. In a propped cantilever loaded as shown in the figure 13.2, the plastic hinges will form at a distance 0.414 L from B. Option C is right answer. Question number 121. For a propped cantilever beam subjected to a point load W at B, if a uniform beam shown in the figure 13.3 has the plastic moment capacity MP for span AB and 0.9 MP for span BC, the correct virtual work equation is given by. So look at the beam, and this is the beam mechanism. Okay. If this angle is theta, this and this angle is 2 theta by 3. So this angle will be theta plus 2 theta by 3. Okay. So by virtual work method, we know external work done WE equal to internal work done WI. So external work done will be load into deflection W into 2 theta, and the internal work will be moment into rotation. So MP into theta plus 0.9 into theta plus 2 theta by 3, because hinge will form here and here. So the internal work done will be at here and at here. Moment capacity MP for span AB and 0.9 MP for span BC. Option C is right answer. Question number 122. At a fully plastic section, infinite rotation can occur at constant plastic moment. Option C is right answer. Question number 123. A simply supported beam of rectangular section and span L is subjected to a uniformly distributed load at the center. The length of elastoplastic zone of the plastic hinge will be. Length of elastoplastic zone of plastic hinge is the length from the point of load application to the end of plastic hinge. Okay, so let's find out what is the length. Suppose this is the rectangular beam subjected to uniformly distributed load W per unit length of total length L. So we know the bending moment diagram will be parabolic. Okay, so if we consider this length, we know the maximum plastic moment will be at here, that is MP, and say the yield moment is here at left side and here at right side My. Okay, so this length will be elastoplastic zone. Okay, suppose this is X. Okay, so we know the formula from parabola, the constant A equal to y by x square. So by the property of symmetry we can write parabola APB is equal to parabola CPD. Okay, so we can write the plastic moment MP by L square, MP by total length L square equal to, for the parabola CPD, the height will be MP minus My divided by this length x square. Okay, x by L square equal to 1 minus My by MP. Okay, My by MP means 1 by shape factor. Okay, so 1 minus 1 by S. So, and if we calculate again, we will get x square equal to L square into 1 minus 1 by S. And for rectangular section, we know the shape factor S will be 1.5. So if we put S equal to 1.5, we will get x equal to L by root 3. Okay, this is the length of elastoplastic zone. Option B is right answer. Question number 1 to 4. The plastic design method is an advantageous replacement over elastic design method for the structures stressed primarily in bending in case of statically loaded structures and indeterminate structures. Both option 1 and 4 are correct. Option B is right answer. Question number 1 to 5. As per IS 800 in the plastic design, which of the following pairs are correctly matched? Working loads and load factor. For dead load, load factor 1.7, dead load plus imposed load, the load factor will be 1.7, and dead load plus imposed load plus load due to wind or seismic force, the load factor will be 1.3, but here not given, so only statement 1 and 2 are correct. Option A is right answer. Question number 1 to 6. The shape factor of an isosceles triangle for bending about axis parallel to the base is 2.34. Option D is right answer. Suppose this is the isosceles triangle ABC. Okay, this is the neutral axis, and say this is D, this is E, and the height of this triangle is H, and this height from here to here is H dash. So this height will be H minus H dash. Okay, so the distance between this axis and CG will be y1, and the distance between this axis and the CG of this bottom portion is y2. Okay, we have to find out the shape factor of this triangle. We know shape factor S equal to ZP by ZD. ZP means plastic section modulus and ZD is the elastic section modulus. ZD is the elastic section modulus which is I by Y max. I is the moment of inertia and Y max is the 2H by 3 of this full triangle. Okay, so if we calculate, we will get ZD equal to 0.042 BH square. Now we know the formula of ZP equal to A by 2 into within bracket Y1 plus Y2. A is the area of this triangle, and Y1 and Y2 we know this distance. Y1 is the distance between this axis and CG of this area, and Y2 is the distance between this axis and CG of this bottom area. Okay, so we can also say this triangle ABC and triangle ADE both are similar, so we can write B dash by H dash. B dash is the width of this triangle ADE and B is the width of this triangle ABC. Okay, so we can write, so B dash divided by H dash equal to B by H. So from here we can write B dash equal to B by H into H dash. Okay, we also know that this is the plastic neutral axis. The area above this axis is equal to the area below this axis. Okay, so area above this axis will be half into B dash into H dash. Okay, which is equal to the half of this triangle, half into B into H. Okay, so if we write this, so H dash will be equal to BH divided by 2B dash, and we got B dash equal to B by H into H dash. So if we put, we will get H dash equal to H by root 2, and similarly B dash equal to B by root 2. Okay, so y1 will be equal to H by root 2 divided by 3. Okay, which is equal to 0.23236H, and y2 will be equal to H minus H dash by 3 into B dash plus 2B divided by B dash plus B, trapezoidal formula. Okay, which will be equal to 0.155H. Okay, so ZP will be equal to A by 2 into y1 plus y2. We know the formula for area of this triangle, half into B into H. So and y1 y2 we know the value, so if we put, we will get ZP equal to 0.098 BH square. Okay, so shape factor S equal to ZP by ZD. We know ZP equal to 0.098 BH square and ZD is the 0.042 BH square. If we calculate, it will be 2.34. Question number 127. In case of plastic design, the calculated maximum shear capacity of a beam as per IS 800 shall be 0.55 AWFY. Option A is right answer, where AW is the effective cross-sectional area resisting shear and Fy is the yield stress of the steel. Question number 128. The allowable stress for the design of steel tanks are taken as 1.25 times the value given in IS 800. Option 2 is correct answer. Question number 129. The minimum thickness of a steel plate which is directly exposed to weather and is not accessible for cleaning and repainting should be 8 mm. Option C is right answer. Question number 130. The moment of inertia of the pair of vertical stiffeners about the center line of the wave should not be less than 1.5 into d cube t cube divided by c square. Option C is right answer, where t is the minimum required thickness of wave and c is the maximum permitted clear distance between the vertical stiffeners for thickness t. Question number 131. The connection of intermediate vertical stiffeners to the wave not subjected to external loads shall be designed for a minimum shear force kilonewton per meter of 125 t square by h. Option C is right answer, where t is the wave thickness in mm and h is the outstand of stiffener in mm. Question number 132. When the vertical intermediate stiffeners are subjected to bending moments due to the eccentricity of vertical loads, their moment of inertia in centimeter to the power 4 is increased by 150 into md square divided by et. Option B is right answer, where m is the applied bending moment in kilonewton meter, d is the overall depth of girder in mm, e is the Young modulus in MPa, and t is the thickness of wave in mm. Question number 133. For a compression member with double angle section, which of the following section will give larger value of minimum radius of gyration? Option B is right answer, unequal legged angles with long legs back to back. Question number 134. Lug angles are used to reduce the length of the connection. Option A is right answer. Question number 135. For rivets in tension with countersunk heads, the tensile value shall be reduced by 33.3%. Option B is right answer. Question number 136. A steel beam supporting the loads from the floor slab as well as from the wall is termed as spandrel beam. Option C is right answer. Question number 137. The pitch of tacking rivets when double angle connected back to back and acting as tension member should not be more than 1000 mm. Option C is right answer. Question number 138. In a moment resistant connection, the moment resistance of riveted connection depends upon tension in rivets. Option C is right answer. Question number 139. The allowable shear stress in the wave of mild steel beam decreases with increases in h by t ratio. Option B is right answer, where h is the height and t is the thickness of the wave. Question number 140. The ratio of the allowable stress in bending compression to that of bending tensile tension in steel beam is less than equal to 1. Option B is right answer. Question number 141. Consider the following statements in respect of design of wave and flange splices. Statements 1. Flange splice shall be designed for actual beam at the section. Right. Statement 2. Flange splice shall be designed to resist the actual shear at the section. No. Statement 3. Wave splice shall be designed to resist actual shear at the section. Right. And wave splice shall be designed for the actual beam. Wrong. So out of these statements only 1 and 3 are correct. Option A is right answer. Question number 142. A base plate of area 6 to 5 cm square has to be provided for an axially loaded column ISMB 200 flange with 100. Which one of the following arrangements shown in the figure 13.4 would result in least base plate thickness? Look, suppose this is the base plate. Okay. Over the slab basis, base plate is provided and the column is standing. Okay. So if this is the column and this is the base plate, so there is a projection here and here. Okay. So longer projection is A and shorter projection is B, and the thickness of this base plate is given by this formula is equal to root over of 3W by sigma Bs into A square minus B square by 4, where W is the pressure from the base and sigma Bs is the permissible bending stress in the slab bases over which the base plate is connected by the nut bolt. Okay, and A is the longer projection of the base plate from the column. Okay, and B is the shorter projection from the base plate of the base plate from the column. Okay, so in the question it is asked that out of these 4 arrangements which would result in least base plate thickness. Look, this is the thickness of the base plate formula, T equal to root over of 3W by sigma Bs into A square minus B square by 4. Okay, so this value is constant, 3W root over of 3W by sigma Bs. Okay, so this value differs, A square minus B square by 4, root over of B square minus B square by 4. Okay, so this is constant K into A square minus B square by 4, root over of A square minus B square by 4. This is our main formula now. Okay, so these 4 conditions 1, 2, 3 and 4. Now we have to determine which arrangement has least base plate thickness. Okay, so for least base plate thickness T, the value of this portion will be less, A square minus root over of A square minus B square by 4. Okay, so let's calculate. For arrangement 1, this is the column, this is the base plate of size 25 cm by 25 cm. The column, this is the column of flange with 100 mm and the height 200 mm. So A is the longer projection. This A will be 7.5 cm and B, the shorter projection, will be 2.5 cm. So if we calculate, T will be equal to K into root over of 7.5 cm square minus 2.5 cm square by 4. So it will be K into 7.3. For the next arrangement, the longer projection will be 5.75 cm and shorter projection will be 5 cm, that is B. Okay, so by this formula T will be equal to K into root over of 5.75 square minus 5 square by 4. It will be 5.1 into K. Next, the arrangement 3, the longer projection A will be 21.25 cm and the shorter projection will be nil because the base plate is connected to the length of the column. Okay, so the thickness will be T equal to K into root over of 21.25 square. The value will be T equal to 21.25 into K. And the arrangement 4, in this case the projection, only one projection will be available, that is here, that is 10.75 cm, and here the projection, here at this point there will be no projection. Okay, so B will be 0. So by this formula, thickness T will be equal to K into root over of 10.75 square. So T will be equal to 10.75 into K. Okay, now for the least possible thickness of base plate, we have to use the least value. So K into 7.3, then K into 5.1. This is the least possible value. So this arrangement will give least possible thickness of base plate. Option B is right answer. Question number 143. Battens provided for a compression member shall be designed to carry a transverse shear equal to 2.5% of the axial force in the member. Option A is right answer. Question number 144. The following observation relate to the designing of the laced column. Single lacing system on opposite planes shall preferably be in the same direction so that one is a shadow of the other. Right. Statement 2. Lacing bar should only be a flat. No. It can be angular in section. Statement 3. The slenderness ratio of the lacing bar for compression shall not exceed 180. No. It is 145. So it's wrong. Statement 4. The laced compression members are to be provided with the tie plates at the ends. Right. So out of these observations, 1 and 4 are correct. Option D is right answer. Question number 145. Look at the figure 13.5. The effective length of the column AB shown in the figure 13.5 is. Look at this frame. AB is the column. Okay. So here is what will be the effective length AB. Just see, here the connection is pin connection and here the connection is fixed connection. So the effective length of AB will be 0.8L because it is effectively held in position at both ends but restrained against rotation at one end. Okay, so the effective length LE will be equal to 0.8 into L. So option C is right answer. The value of effective length LE will be equal to greater than 0.7 L but less than L. Question number 146. Match list 1 with list 2 and select the correct answer using the codes given below. The list 1 types of stress and list 2 allowable value of stress. A. Axial tension 0.60 Fy. Option 3 in list 2. In list 1 bending tension. List 2 it will be 0.68 Fy. In list 2. In list 1 maximum shear stress will be equal to 0.40 Fy. Option 4 in list 2. And the bearing stress in list 1 will be equal to 0.75 into Fy. In list 2 Fy is the minimum yield stress of steel. So the arrangements are B. Option B is right answer. Question number 147. A portal frame subjected to central concentrated load and horizontal load is shown in the figure 13.6. Likely positions where plastic hinges can form in combined mechanism would include. So in this portal frame the plastic hinge will occur at 1, 4 and 5. These three positions because the plastic hinge will occur at the point load, okay, and at the change of geometry like 2 MP to MP or MP to 2 MP. So this point will be valid. Here plastic hinge will occur and at this point the plastic hinge will occur because the point load is here, and also there will be a plastic hinge at this point because the section is changes from 2 MP plastic moment capacity to MP. So here plastic hinge will occur. Option B is right answer. Question number 148. 3 types of continuous beam supporting a concentrated load at the central span are shown in the figure 13.7. The collapse load PU corresponding to figure 13.7 A, B, C respectively are P1, P2 and P3. Which one of the following conclusions is correct? 3 types of continuous beams are shown. So we have to analyze it one by one. Okay, and find out the relation between P1, P2 and P3. Okay. So for continuous beam 1, A, B, C, D, the plastic hinge will form at B and C and at the point of loading. Okay, P1. So the beam mechanism will be like this. Theta, this angle theta, this angle theta, and this angle is theta plus theta. So external work done will be load into deflection, P1 into L by 2 into theta, and internal work done Wi will be equal to moment into rotation, MP. Here the section plastic moment capacity is MP into rotation theta, MP theta plus MP into theta plus theta plus MP into this angle theta. Okay, So by virtual work method we know external work done equal to internal work done. So WE equal to WI. We will get P1 equal to 8 MP by L. Similarly for continuous beam 2 DEFG. Okay. All the span has a moment capacity of MP. Plastic moment capacity of MP. Okay. So if we draw the beam mechanism, because plastic hinge will form at E and F and at this point of loading. Okay. So the external work done W equal to load into deflection L by 2 into theta. This length is L by 2 middle, and internal work done will be moment into rotation. So here it will be MP into theta plus MP into theta plus theta, and here MP into theta. So if we equate by the method of virtual work, we will get P2 equal to 8 MP by L. And for continuous beam 3 MNOP subjected to a loading P3 at the middle portion. Okay. If we draw the beam mechanism, the plastic hinge will form at N, O and at this point of loading. So if we draw the beam mechanism, we will get external work done equal to load into deflection P3 into L by 2 into theta, and internal work done equal to MP into theta plus MP into theta plus theta plus MP into theta. So if we equate external work done equal to internal work done by the method of virtual work, we will get P3 equal to 8 MP by L. Okay. So from equation 1, 2 and 3, from equation 1, 2 and 3, we can say P1 equal to P2 equal to P3. Option C is right answer. Question number 149. For a certain longitudinal span, a beam in an industrial building requires section modulus of 4 to 3 cm3. Which one of the following sets of section would be most suitable for this purpose? The section modulus requirement is 4 to 3 cm3. Okay. So the industrial building purpose, the section is I section. So the shape factor is 1.15. Plastic section modulus, that will be equal to 423 into 1.15, which is equal to nearly 487 centimeter cube. So Z axis will be suitable 488.9 centimeter cube. Okay. So we can use ISLB 300 at the rate 37.7 kg per meter. Okay. Option B is right answer. Indian Standard Light Beam. Question number 150. The channels or angles in the compression cords of the steel truss girder bridges are turned outwards in order to increase the radius of gyration. Option D is right answer.